Hello everyone, my name is Scott Young and this is a presentation about our team's work with CAS Atlantic at the University of New Brunswick. Modern software often needs to run on many machines, which do not always share common architecture. For example, customers want to be able to check their emails on their phones, workstations, laptops, and personal computers. Rather than write an individual application for every possible device a customer might use, software developers target managed runtime environments instead. When considering a managed runtime environment, a key factor is performance. Performance is often sacrificed in exchange for portability. This trade-off is due to the application running one layer above the bare metal in a managed runtime, usually through the process of interpretation. To combat the performance concerns of a managed environment, many different solutions have been proposed and researched. The most prevalent and successful solution employed is that of a just-in-time or JIT compiler. A JIT compiler operates in the background of the managed runtime to identify critical areas of the application that are used frequently. Upon identifying the critical areas, it pauses the managed runtime and generates code for the host machine to natively perform an equivalent task. The environment is unpaused and the native method is now invoked in future execution to accelerate performance. There are multiple types of JIT compilers, but two common examples are optimizing and templated. An optimizing JIT compiler uses insights about the code it's compiling to create code that runs as efficiently as possible, at the cost of increasing the time it takes to compile code. A templated JIT compiler always creates the same block of code for a given instruction and emphasizes the rate at which it can compile functions instead. Our project aims to include a templated just-in-time compiler into the Eclipse OpenJ9 Java virtual machine. OpenJ9 currently uses an optimizing JIT compiler called Testarossa, or TR for short. An optimizing compiler has to be selective in what code it will compile, because of its long compile times. This means that some methods are executed by the interpreter a number of times before they are chosen as a candidate to compile. A templating compiler generates code that is faster than interpreting, but usually slower than an optimizing JIT compiler. However, they compile quite quickly and also require less memory to compile a method because it needs to know less information to perform its job. This highlights two specific use cases for a templated compiler in OpenJ9. Porting OpenJ9 to resource-constrained environments, such as IoT gateways, and speeding up applications between the time that they are launched and when TR can optimize them. We introduced the concept of MicroJIT, a templated JIT compiler with support for interaction with TR. MicroJIT is asynchronous, allowing code to compile without pausing the interpreter. MicroJIT currently targets the x86-64 architecture, but has been designed to allow easy porting to other architectures supported by OpenJ9, such as AArch64. MicroJIT is a work in progress, and as such does not yet support all of the Java bytecodes that can be read by the OpenJ9 Java virtual machine. However, we are working on supporting more of them and adding profiling instructions to allow TR's optimizer to correctly identify the critical sections of code even when MicroJIT compiles them first. MicroJIT can also avoid creating many of TR's supporting data structures, such as its intermediary language. Finally, future work on our roadmap will be to create a simplified interface to MicroJIT to allow developers to port a version of it to their own runtime and include it in the Eclipse runtime library, OMR. There is a lot of work ahead for the MicroJIT team. As a passionate group of researchers, we're excited about the opportunities for this project and the impact it can have on the world. Thank you for attending our presentation.